Entropy number one. Okay, so this is entropy part one, number one. And I have that right here. It says, so a gas expands isothermally. What does isothermal mean? That's right. The temperature stays the same. Um, it's an internally reversible process. Um, so we start out with a pressure P1 of 14 bar and a temperature of 60 degrees Celsius. And it ends up with a pressure of 2.8 bar and the same temperature. Um, and you're supposed to do it with two different materials. Let's just do, so we're supposed to do it with refrigerant 134A and with air as an ideal gas. Let's see. I don't think I have any of those values with me. Let's just go through it generally, see what we end up with, and then, yes. Yeah. You would have to do that to calculate it, but so just use, we've used that a few times for air, so just use that value. That's a value you can just Google. But if you wanted to calculate it on your own, yeah, you'd have to figure out the percentage that's nitrogen, use the molar mass of nitrogen, right. Um, so we're going to determine uh, heat transfer and the work. So we're just calculating Q and W. Okay, well, to calculate the heat transfer, okay, so it expands. The heat transfer. Okay, so we have basically three equations that are candidates to use. One is the first law. So that says that the change in energy is equal to Q minus W. And it doesn't say anything about this changing speeds or changing heights or anything. So I'm just going to replace this change in energy with change in internal energy. And then the second and third equations are the TDS equations. So I'll use the specific one. So TDS is equal to du plus p dv. And then the third one says TDS is equal to dH minus v dp. Okay, so if we're trying to come up with finite changes, we're going to be integrating those TDS equations. So let me rewrite each of these. So we have the integral of TDS is equal to the integral of du plus the integral of p dv. And the second one says the integral of TDS is equal to du minus the integral of VDP. Okay, we're trying to figure out a way to come up with the heat transfer and the work. We can use tables, like we have everything we need to know about the states in both of these cases, no matter what material we're using, right? So we can calculate the, not calculate, from the table, we can just look up ending values of entropy, internal energy. Yes. Mm-hmm. You're right. Okay, so let me keep going with 2 and 3 here. Okay, so if you take this integral, temperature constant, so that's nice. We can pull the temperature out of the integral. So we have T times the integral of ds, which is, I'm going to write that as S2 minus S1, is equal to U2 minus U1 plus we don't have pressure given as a function of volume here, but I think the main thing you have to notice in this problem is, here's U. So that integral PDV, we can probably put that in a form where we can use that to calculate the work. Everything else we can look up. The third equation, let's see if that gives us anything good. So integrate that, you get T times the quantity S2 minus S1 is equal to the quantity H2 minus H1 minus this thing. We don't have V as a function of P. That's just a mess. So let's put our eggs into the basket of this one. And let's set that one aside for now. Okay, so PDV is equal to P d capital V over the mass, and the mass stays constant over this whole thing. So the integral of P d little v is equal to 1 over the mass times the integral of P d big V, and that is equal to W over M. And so integral of PDV, like integral for work that we want. Yeah, exactly. Okay. Right. So that's how we came from this integral to just replacing it with work over M. Right. And so so this equation, the boxed equation, now says T times S2 minus S1 is equal to the quantity U2 minus U1 plus work over mass. This is the only unknown. Because we can look up the entropies and the internal energies in the table, no matter which one of these two we're using. If we're using the refrigerant, we can just look them up directly. If we're doing, what was it, air? If we're doing air as an ideal gas, then we have to calculate it using that S0 thing, but not too hard to do. Question? This is most likely, I mean, unless it happens to be at saturation, you have to use both of those to get it. Yeah, so remember there's the three different tables. It's either a liquid below the saturation temperature, or it's at saturation, or it's a superheated vapor. This is most likely a superheated vapor, so you have to use both of those. But you can check if you have the temperature and pressure both like this. You can just quickly glance at the saturation table. It tells you what the, so go to 60 degrees Celsius in the saturation table. Look and see if the pressure there matches this. If it doesn't, then you need the other table. Okay, so work. We're trying to calculate work over mass. Is that right? No, just total work. So work is equal to T M times S2 minus S1 minus M times the quantity U2 minus U1. That's all stuff you can look up. We're not given a mass in this problem, so I guess you're just going to have to give the answer per mass. Okay, and then, well, this was actually part B. I think that's probably, you have to go get that one first. But then we can go to the first law. The first law says the change in internal energy is equal to Q minus W. So Q is equal to internal energy plus W. Now we have an expression for W. We can just look up this value of internal energy. We already looked up the two end values. And so then you can just calculate Q. Any other questions about that one? Yes. Yeah, I don't have that one written here. Anybody have it? No. Anybody have it down? No, just have the question. Okay, so number 6. Okay, number 2. So you have air in a piston cylinder. And it undergoes a Carnot power cycle. There are 4 stages in the Carnot power cycle. And 2 of those are isothermal. So the isothermal expansion is at 1400 Kelvin. The isothermal compression so it's isothermal. So this is T1 and that's also T2. For the isothermal compression, T1 is 350 Kelvin. And isothermal means that's also the T2. And for the compression, we have a pressure P1 of 100 kilopascals. That's 1 bar. And a pressure P2 of 500 kilopascals. So 5 bar. We're going to treat air as an ideal gas. And we're going to assume, this is an ideal gas where Cp is constant. .005 kilojoules per kilogram Kelvin. And we want to figure out the pressure at the beginning and end of the isothermal expansion and second, the heat transfer and work for each process. And third, the thermal efficiency. Okay. Well, this is an ideal gas. So we're going to use, and not only is it an ideal gas, it's an ideal gas where the specific heat C sub P is more or less constant. So let's see, what did we get for ideal gases? If you start with the TDS equations, you can come up with pretty simple equations for the change in entropy if those specific heats are constant. So how does that work? So we have somewhere in your notes you have this, so you can rescue me at any time if you like, or you can just watch me try to do this. So TDS is equal to du plus PdV. For an ideal gas, P is equal to RT over V. Yeah, I'm already making good progress here. Yeah, that's probably, so yeah, so tell me that one again. Cp dt over T over P. Okay, not from this one. Right, you're right. So this is actually from the other one. Okay, and now, let's see, we're going to integrate this, and it's isothermal. Each of these two is isothermal. So this goes away. There's no change in temperature. And so we get that S2 minus S1 is equal to negative R natural log of P2 over P1. And for an ideal gas, we can calculate, like we can look this up in a table in terms of the S zeros. Can someone tell me what the expression is for the change in entropy with the S0 expressions? Okay, that's not times, that's a function. That's an argument, you know what I mean? So yeah, S0 at T2 minus S0 at T1, and then minus T2 over T1. P? Huh, P2 over P1. Okay, so that means that this cancels with this. Oh, that's just so great. And we have that the change in entropy is equal to S0 at T2 minus S0 at T1. Okay, so we can look up those values of entropy. So we have everything we need to get the change in entropy. Okay, so we're trying to calculate the pressures, but the pressure has disappeared here. Um, okay, so let's
So the change in entropy equation, isn't it just change in entropy is equal to S zero at temperature 2 minus S zero at temperature 1 minus R ln of PT over P1? Like that shouldn't have dropped out.
but so from the from using the TDS equation for so starting with the TDS equation, making the assumption of ideal gas, we got that ds was equal to negative R dP over P. And so when I set those two things equal, the
PT over P is 0.
no, it's isothermal in both of these, right? Isothermal expansion and isothermal compression. Those aren't the only, okay, so those are two separate processes that are not adjacent to each other. So there's a there's an adiabatic compression, an isothermal compression, an adiabatic expansion, and an isothermal expansion. And so those two things aren't happening right next to each other, you know. But for each of those two individual isothermal processes, the temperature is constant. Um, isothermal, so there is heat transfer for both of these. Um, And this is a reversible cycle. It's a Carnot cycle, so all of these things are reversible. And so the definition of the change in entropy is the integral from state 1 to state 2 of dq over temperature for an internally reversible cycle, but that's what we have here. Okay, so can we figure that out? So we can look up, so we know these are from the table. And this is a transfer of an amount Q over a temperature of well, if T1 and T1 and T2 are the same, so those are going to be the same. So this 0. Isothermal. So, I mean, if it's isothermal, there's no change in temperature. We're thinking of during each of these individual processes. So there can't be any change in temperature. So dT has to be 0. Oh, and okay, so these two things I think that was like sort of circular logic, right? Those are coming from the same place. Okay, so let me go back to this. Okay, so the change in entropy is this, and that is equal to the integral from state 1 to state 2 of dq over temperature for an internally reversible process, which we have. And so this is equal to the transfer Q divided by the temperature. And so if we, okay, so let's do one of these two. Well, one of these two, okay, so here's where this is going. There are four stages of a Carnot cycle, okay? 2 are isothermal and 2 are adiabatic. Adiabatic means there's no heat transfer, okay? So for the 2 isothermal processes, there is heat transfer, and somehow we're going to have to figure out, be careful about this, but like the energy that's coming in for one of the isothermal processes has to be the energy that goes out for the other isothermal process because it's a cycle. What kind of energy can that be? We have to be careful about that. But probably, I'm thinking we're going to calculate the Q value the heat transfer for the one where we know the two ending pressures. And then we're going to use that in some way to let us calculate the pressures in the other one, because something about that Q is going to have to be like equal and opposite. Okay. All right. So, all right. So let's do it for the one where we know all the stuff is the isothermal compression. And so for the isothermal compression, we have negative R times the natural log of pressure 2 over pressure 1. So that's 5 over 1 is equal to Q over the temperature, which is 350 Kelvin. And so Q is equal to negative 350 natural log of 5. We know this R. Okay, so we know the heat transfer for the isothermal compression. Now let's think about the work. So how are we going to get work? The most likely thing is we're going to have to use the first law for that. That's the way we normally have to relate work and heat. So the first law says the change in internal energy is equal to Q minus W. What do we know about internal energy for an ideal gas? We're treating this as an ideal gas. There's something important there. It's dependent on only one property. What's that property? Temperature, yeah. So U is a function of temperature only. And so if it's isothermal, then we know that there's no change in internal energy. So that means Q is equal to W. So our work is also negative 350 times R times the natural log of 5. Might as well plug in this R. This is for air. You just said what it was before, right? 29 times 10 to the minus third. Oh, yeah. Okay, so negative 350 times, can you multiply that out? 286? Okay, 286.7 times natural log of 5. And what do you get for that? Negative what? 161,493. Okay. Okay, so that means that work is also negative 161,493.22. Okay, so do the signs make sense for Q and W? Yes, this is a compression. So Q, well, Okay, so first for work in a compression, um, it has to be negative. And now for the heat, what happens if it's adiabatic, if it's insulated and you compress a gas, what happens to its temperature? The temperature goes up as you compress it. And so if you're keeping the temperature the same using heat transfer, heat has to transfer out of the gas. So that makes sense. Okay, so we're on the right track now. This is hard. Holy moly. Okay, so uh, we have everything we need to have about the thermal compression. So now let's go to the expansion. This one's different because we're not given the pressures. So we don't know those. But we do know, so what's the stuff that we can use from the first one? Um, so everything, everything we did from the TDS equation, this is all still valid. So we still know that Q over T is equal to negative R times the natural log of P2 over P1. It's just that this time we don't know what P1 and P2 are. And we still know the same thing that we got from the first law. We still know that Q is equal to W. Okay, so um, let's start with this equation, the TDS equation. Yep. Yeah, if those were the only two stages, that would definitely be true. But I think it, I can't see why it would be true. It might be true, but I can't see why it would be if there's two different stages happening, in between them. Okay, so let me look at this equation for a second. So we have TDS is equal to du plus P dV. And so ds is equal to du over temperature plus 1 over temperature P dV. And that is, so ds is equal to du over T plus 1 over the mass times the temperature times P big V. So the change in entropy is equal to 1 over the temperature times the change in internal energy plus 1 over the mass times the temperature times the work. Um, so what if we use this other uh, so CP CP is equal to du dt. Well, yeah, of course, this just goes away. Um, okay, I'm gonna have to get back to you on that one. I don't think I'm gonna solve this. Nothing jumps out at anybody, right? I sort of have the feeling that something you were talking about is right, but I just can't understand why it would be. You know what I mean? Like it seems like we need to use some of the symmetry of this somehow, but uh-huh, right. Yeah, right. Yeah, it does make sort of intuitive sense, but I'm sort of hazy on it. But I'll look that up. I'll either post something on D2L or do it next time or whatever. Okay. Any other questions about that one regarding any of the stuff we did? The part we did for the isothermal compression feels totally right. I don't have any concerns about that. I don't really know where to go on this one. Uh, so let's go back. Whose sheet was this? Um, so let me just give like sort of a refresher of where we are in the second law stuff. Um, So the second law of thermodynamics so far, these are the big equations. So the first one is the mathematical form of the Kelvin-Planck statement. And that says if you have a cycle and your system is in contact with just one thermal reservoir, then the work done by that cycle is less than or equal to 0. And what is required for that to be equal to 0? Internally reversible. So we only care about our system. We don't care whether the surroundings, the things touching it, are reversible. And then second is the Clausius inequality. So that one says for any cycle, it doesn't say anything, make any restrictions on the reservoirs you're in contact with, but for any cycle, if you integrate over the whole cycle, dq over the temperature at the boundary, this integral comes out to be less than or equal to 0. And what are the conditions where it's equal to 0? It is. It's the exact same thing. And the way you can remember that is that the way we derived this was using the Kelvin-Planck statement. And so it came right in at the same restrictions. 0, 4, internally reversible process. And then from that, we defined entropy. And the entropy definition uses the same integral idea, but this time it's from one state to another. So the change in entropy is equal to the integral from state 1 to state 2 of dq over temperature. And are there any restrictions on how you calculate that? Is that our specific cycle, or is that for some kind of ideal cycle? This one is actually for a reversible cycle. This has to be internally reversible. Yes, that's right. That's right. And so then that's the last one I want to do. That's the entropy balance equation. And that says that the change in entropy is equal to this integral from state 1 to state 2 of dq over t around the boundary plus sigma. And this time we're doing the integral for our actual process. And this is the entropy production. And it has to be greater than 0. Okay, so how do you know? Let me try to say this in a way that you'll remember that the definition of entropy depends on an ideal process. So say that you have, at one instant, you have a blob of pudding at a temperature well, it doesn't matter the temperature, whatever. You have a blob of pudding in some environment and it has a certain amount of entropy, okay? And then at a later instant, this blob of pudding has a different amount of entropy, okay? Now, how do you get from this state to this state? There's infinitely many ways you could do it, right? And some of those ways involve running it through a 1950s tractor, you know, super inefficient, loud, smoke everywhere, you know what I mean? And some of those ways involve reversible cycles where everything works perfectly, okay? Would you expect that integral to be the same in all of those cases? It's not, right? And so what that would be saying is that the entropy of this pudding at state 1 and this pudding at state 2 would be different depending on the process you use. And we know that's not the case. We know that entropy is just something you can look up in a table. And that table doesn't care anything about the process. You know what I mean? And so in some sense, it has to be an ideal process that integral depends on to calculate the entropy. Otherwise, when the pudding that you ran through the John Deere tractor is exactly the same state as the one you ran through the reversible cycle. So those entropies should be the same, but those integrals would be different. So that's impossible. Okay, so now we're going to use this idea. So next, we're going to use this entropy production idea to determine the directionality of processes. So notice that when you use conservation of energy, you don't know anything about the direction that things go. So if you first think about a frictionless skateboard, someone riding down a hill, okay, they start at rest at the top of the hill. You can calculate their speed at the bottom of the hill. You could just as easily calculate their speed at the bottom of the hill and figure out that they would get up to the top and be at rest. There's no way to determine which of those happens earlier or later, okay? And using energy balance, that's also true if you include friction and things like that, because you're just adding a work term by the friction or whatever, and you can go either direction. But now we're going to use this idea that um, since now we have a way to calculate entropy production, we know that forward in time means positive entropy production. Okay. So now, like, if someone goes down the hill on a skateboard and there's friction, if we could calculate the entropy production over that motion, we could say, okay, well, this process didn't go backwards because entropy production would have to be negative, and that's impossible. Okay. So what we need for this is well, we need this to be an isolated system. And that means two things. First, it means no material transfers across the boundary. And second, no energy transfer across the boundary. An easy way to do this is to just keep your system in a rigid, isolated, insulated container. So keep the materials that you're analyzing in a rigid, insulated container. Then for this isolated system, well, there's no heat transfer across the boundary. And so the change in entropy isolated is just equal to the entropy production and that has to be greater than or equal to 0. This is probably the most concise form of the second law entropy statement. Because the universe is an isolated system. And so for that isolated system, in any process that happens in the universe increases the entropy of the universe. Okay, so let's do an example. So let's say we have an isolated system with 0.5 kilograms of steel that's bathed in 10 kilograms of liquid water. And we're going to assume both of these are incompressible. And incompressible means that we can just talk about specific heats as a single value. The specific heat for the liquid water is 4186 joules per kilogram Kelvin. And for the steel, it's 460 joules per kilogram Kelvin. And let's say there are two states. The first one is the steel at 400 degrees Kelvin, and the water at 283 Kelvin. And the second one is the steel at, well, same temperature. So first, what's that temperature when they're the same? And second, which of these two states happens first and which happens last? Intuitively, this is a pretty simple process. We're not dealing with work or anything, so we're pretty used to thinking of things like this. Which one is gonna happen first? They're gonna have different temperatures at the start, and then slowly it's gonna turn into equilibrium. You never put two things at the same temperature together and then take one out and it's like hot and the other thing's cold. Um, and really, that's because of the Clausius statement. It's a simple thing to understand. It's just heat transfers from the higher temperature thing to the lower temperature thing until there's no difference between them. So this isn't a case where it's really necessary to figure for the directionality to use the entropy production, but this will show like the approach that you'd use in a more complicated thing. All right, so how are we going to calculate this? They're both incompressible, and so for incompressible, the specific heat is equal to the derivative of U with respect to temperature. And so du is equal to C dt. And so the change in internal energy is equal to C times the change in temperature. This system is isolated. So the total change in internal energy has to be equal to 0. And so what we get thinking about it this way is the calorimetry equation that you've probably used in chemistry and maybe a little bit in physics. But it just says that 4186 and actually this is wrong. This needs to be the extrinsic value of internal energy. So we just have to multiply a mass on there. So we have the specific heat of water times the mass of the water that we have, times the temperature final minus the temperature initial. The temperature initial for the water. And then we'll add that to the change in energy for the steel bar. So that's 5 times 460 times T final minus T initial for the steel. And those have to add up to 0. So 41,860 times T final minus 283 plus 230 times the quantity T final minus 400 equals 0. And you can solve for T final. And you get the T final is equal to basically 283.6 Kelvin. Okay, so that's the equilibrium temperature it's going to be, and I wrote it like that's going to be the final temperature, but it doesn't matter. We could have done it with calling that the initial temperature, and you'd get the same value. That equation doesn't know anything about what happens before and after. But now we're going to use entropy production idea. Remember, for incompressible, the change in entropy is equal to the specific heat times the natural log of the temperature later minus the temperature earlier. And we know that for an isolated system, the total change in entropy is just equal to the entropy production. And so now we can try out these two possibilities. So possibility 1. The materials start at different temperatures and then equilibrate. This is the one that we expect to be possible. So we're going to calculate the change in entropy for the whole system. So that's going to be, so the change in entropy for the isolated system is the change in entropy for the water plus the change in entropy for the steel. And that is 3186 times the natural log of our later temperature in this possibility would be 283.6, and our earlier would be 283. And then add that to 460. Oh, and we need the mass still because this would be, I'm sorry, this would be specific. So need the 10. So 10 times 41. So go back and change this. Be careful about this. I wrote this wrong. So for an incompressible material, change in specific entropy is equal to this. And that means that the change in extrinsic entropy would be mass times specific heat times natural log of T2 over T1. Okay, and add that to the mass of the steel, 0.5, times its specific heat, 460, times the natural log of its later temperature, 283.6, over 400. And can someone calculate each of these two terms by themselves? Okay, and the second one? And negative, right? So, 0.9. 0.9. Negative. And so you come out with a total of 9.56. Okay, so this positive means that this is the way that it goes. Okay. So this is the correct direction. Okay, this won't take very long, but let's think about what would happen in the case of possibility 2. They both start at 283.6 Kelvin and then change temperatures. Well, then we'll be adding up the entropy of the water plus the entropy of the steel. So that's going to be 10 times 4186 times natural log of, this time what's the later temperature? It's 283 this time. The earlier temperature is 283.6. Add that to 0.5 times 460 times natural log of, this time 400 is the later temperature, 283 is the 283.6 is the earlier. And so now this one is negative, this one is positive, and you get an answer of negative 9.56. And that's impossible. Any questions? Okay. Can you put your binders up on this table as you go? If you don't have them today, just bring them in Tuesday or whatever.